A space documentary script. Picture this. You're standing on a world where diamonds rain from the sky. Where the very air would crush you instantly. Where a year passes in less time than it takes you to watch a movie. This isn't science fiction. This is HD 189733b, and it's real. Somewhere out there, 63 light-years from Earth, orbiting a star in the constellation Vulpecula, there exists a planet so bizarre, so utterly alien, that it challenges everything we thought we knew about planetary science. A world where the wind screams at 4,500 miles per hour. Where molten glass sidewinds through the atmosphere at speeds that would make a jet fighter look stationary. Where the temperature swings so wildly between day and night that entire weather systems form and dissolve in hours. And here's the thing that should make your brain itch. We found it. We actually found it. Let me take you back to 2005. The Hubble Space Telescope, that magnificent eye we placed above Earth's atmosphere, turned its gaze toward an unremarkable orange dwarf star. What it saw would rewrite textbooks. What it saw would haunt astronomers' dreams. What it saw was a planet that shouldn't exist. HD 189733b. Even its name sounds alien. But names don't capture the sheer impossibility of this world. This is a gas giant, slightly larger than Jupiter, our solar system's heavyweight champion. But unlike Jupiter, which orbits the Sun at a comfortable 5 astronomical units, HD 189733b hugs its parent star at a distance of just 3 million miles. That's 30 times closer than Mercury is to our Sun. That's so close that the planet completes an entire orbit in just 2.2 days. Think about that for a moment. A year on HD 189733b lasts 53 hours. You could celebrate your birthday twice in a single Earth week. You could witness 1,000 sunrises before your next dentist appointment. Time itself becomes meaningless on a world that moves so fast. But speed is just the beginning of this planet's strangeness. The first thing you'd notice if you could somehow stand on this world, assuming you weren't instantly vaporized, would be the sky. Not the comforting blue we take for granted here on Earth. Not the salmon pink of Mars or the butterscotch haze of Titan. The sky of HD 189733b is a deep, cobalt blue. Azure. The color of a perfect summer afternoon on Earth. Except there's nothing perfect about it. That blue comes from silicate particles suspended in the atmosphere. Tiny fragments of what would be glass or sand on Earth, floating in the upper atmosphere like microscopic daggers. When the star's light hits these particles, they scatter blue wavelengths, creating that deceptively peaceful azure hue. But here's where physics gets vicious. Those same particles are caught in supersonic winds, transformed into projectiles moving faster than bullets. Imagine standing in a sandblaster that's been cranked up to 11,000 miles per hour. That's not weather. That's annihilation. The glass doesn't fall as rain. It sidewinds. It moves horizontally at speeds that would tear apart any spacecraft we've ever built. And because the planet is tidally locked to its star, one side forever facing the inferno, these winds race from the permanent day side to the permanent night side in an endless, screaming loop. Tidally locked. Let's pause on that concept because it's crucial to understanding just how alien this world truly is. You know how the moon always shows us the same face? That's tidal locking. The same gravitational forces that create ocean tides on Earth have synchronized the moon's rotation with its orbit. HD 189733b suffers the same fate, but with far more dramatic consequences. One hemisphere of this planet stares eternally at its sun, baking under relentless stellar radiation at temperatures exceeding 1700 degrees Fahrenheit. Hot enough to melt rock. Hot enough to boil titanium. On this day side, molecules literally tear apart. Water vapor, if it existed, would instantly separate into hydrogen and oxygen. Any solid surface would glow red hot. Meanwhile, the night side, forever hidden from the star's light, plunges into darkness. But don't think this brings relief. The night side still registers at around 900 degrees Fahrenheit, heated by those apocalyptic winds carrying thermal energy from the day side. Even in eternal darkness, this is a world of fire. But temperature is just one variable in the equation of impossibility that defines HD 189733b. Let's talk about what happens between these two extremes, at the terminator line, that twilight zone where day meets night in permanent standoff. This is where the planet's atmosphere goes completely insane. Picture the boundary between frozen winter and blazing summer compressed into a region just a few hundred miles wide. On one side, you have gas heated to the point where atoms vibrate with such ferocity they emit X-rays. On the other, you have relatively cooler gas still hot enough to incinerate anything we could build. The temperature gradient is so steep, the pressure differential so extreme, that winds accelerate to velocities that make Earth's hurricanes look like a gentle breeze. And these aren't normal winds. On Earth, our fastest winds, found in jet streams and inside tornadoes, might reach 300 miles per hour. Maybe. The winds on HD 189733b exceed 4,500 miles per hour. That's more than 5 times the speed of sound. These winds are supersonic. Hypersonic. There's shock waves propagating through an atmosphere under such stress that the very concept of weather as we understand it breaks down. Now, let's add another layer of nightmare fuel to this scenario. Those silicate particles I mentioned earlier. Under the extreme temperatures of the day side, they don't just exist as solid fragments. They vaporize. Silicates, the stuff that makes up rocks and sand on Earth, transform into gas. And when these silicate vapors get caught in those hypersonic winds and transported to the cooler night side, they condense. They solidify. They form tiny crystals. Glass crystals. Diamond-hard fragments of silicon dioxide suspended in the upper atmosphere. This is where we get the glass rain. Except it's not rain in any sense we'd recognize. These particles don't fall gently. They're projectiles, accelerated by winds moving at Mach 6, sidewinding through the atmosphere in sheets of crystalline death. If you could somehow survive the heat, the pressure, the radiation, you'd be shredded by glass moving faster than rifle bullets. And we know this. We know this with certainty because we measured it. In 2007, NASA pointed the Spitzer Space Telescope at HD 189733b. Spitzer works in the infrared, detecting heat rather than visible light. Over the course of 33 hours, Spitzer watched this planet complete an entire orbit, measuring how its brightness changed as different parts of the planet faced Earth. What they found was unprecedented. The planet was brightest not at local noon, not when the day side faced us directly, but offset by about 30 degrees. The hottest point on the planet was shifted eastward from the subsolar point. This was the first time, the very first time, that we had mapped the temperature of an exoplanet. And that offset told us everything we needed to know about those winds. The only way the hottest spot could be shifted is if winds were transporting heat faster than the planet rotates. Hypersonic winds, confirmed not through speculation but through observation. Through data. Through science. But Spitzer gave us another gift, another piece of this cosmic puzzle. It measured the planet's spectrum, breaking down its light into component wavelengths, each one telling a story about the molecules present in the atmosphere. And what it found defied expectations. Water vapor. Carbon monoxide. Carbon dioxide. Methane. But these molecules weren't distributed evenly. They weren't behaving the way models predicted. The day side showed different chemistry than the night side. Molecules were being created and destroyed in real time, torn apart by heat and reformed by pressure, creating a dynamic chemistry lab the size of a planet. Let me put this in perspective. On Earth, our weather is driven by temperature differences of maybe 50 or 60 degrees between the equator and the poles. That's enough to create hurricanes, tornadoes, monsoons, the entire chaotic dance of Earth's climate. HD 189733b has temperature differences of 800 degrees between its hemispheres. 800. The energy available to drive atmospheric circulation is almost beyond calculation. The planet's entire atmosphere is essentially one giant heat engine, converting thermal energy into kinetic energy with efficiency that would make an engineer weep. Now here's where things get even stranger. Remember, this is a gas giant. There's no solid surface. What we're talking about, what we're describing, is atmosphere all the way down. The surface of HD 189733b, if you could define such a thing, would be the altitude where atmospheric pressure reaches 1 bar, the same pressure we experience at sea level on Earth. But on this planet, at that altitude, you'd be surrounded by gas at 1700 degrees Fahrenheit. And as you descended deeper, the pressure would increase exponentially. 10 bars. 100 bars. 1,000 bars. At some point, probably around a few thousand bars of pressure, the hydrogen and helium that make up most of the planet would transition from gas to liquid. Not through cooling, but through compression. The pressure would be so intense that atoms would be forced together despite the screaming temperature, creating a fluid that doesn't exist anywhere on Earth. Liquid metallic hydrogen, a state of matter so exotic that we can barely recreate it in laboratories for fractions of a second. And deeper still, beneath layers of liquid metal hydrogen, there might be a core. Not might. Almost certainly. Probably composed of heavier elements, rock and metal compressed to densities that would make lead look fluffy. This core might be 10 or 15 times the mass of Earth, squeezed into a sphere not much larger than our planet. The pressure at the center would be in the millions of bars. The temperature would exceed that of the Sun's surface. This isn't just an alien world. This is an alien universe, compacted into a sphere roughly the size of Jupiter. But let's come back to what we can actually observe, because here's where HD 189733b throws another curveball at us. In 2008, astronomers using Hubble made a detection that should have been impossible. They found sodium in the planet's atmosphere. But not just traces. They found sodium in absorption, meaning the planet's atmosphere was so extended, so bloated, that it created spectral lines visible from Earth. And that tells us something profound. This planet is evaporating. Think about that. The star's radiation is so intense, the planet's gravity so weakened by tidal forces and atmospheric heating, that the atmosphere itself is escaping into space. Atoms are being stripped away, particle by particle, creating a tail of gas that streams behind the planet like a comet. Every second, thousands of tons of atmosphere are lost to the void. It's imperceptible on human timescales, but over millions of years, this planet is slowly being devoured by its star. This process, atmospheric erosion, is probably common for hot Jupiters, these gas giants that orbit terrifyingly close to their parent stars. We think many of them started further out, forming in the cooler regions of their solar systems where ice and gas could accumulate. But then something happened. Gravitational interactions, perhaps with other planets, perhaps with the protoplanetary disk itself, caused them to spiral inward. And as they migrated, they entered regions where stellar radiation became weapon-grade, where tidal forces became overwhelming, where survival meant constant atmospheric loss. HD 189733b might have been twice its current size when it formed. It might have had moons, rings, an entire system of satellites. All gone now, either stripped away or destroyed by tidal forces. What we see today is a planet in the process of being murdered by its star, fighting a battle it cannot win, losing mass with every passing second. And yet, paradoxically, it's stable. For now. The planet will likely survive for billions of years, even as it slowly evaporates, a cosmic prisoner sentenced to eternal torment. But here's what really keeps astronomers up at night. HD 189733b isn't unique. It's not even particularly unusual. Since its discovery, we've found thousands of exoplanets, and a significant fraction of them are hot Jupiters orbiting terrifyingly close to their stars. Some are even more extreme. WASP-12b, for instance, orbits so close to its star that it's being actively stretched by tidal forces, deformed into an egg shape, and losing mass at a rate that will completely destroy it in about 10 million years. WASP 76b has temperatures so extreme that iron vaporizes on the day side and condenses on the night side, creating literal iron rain. We found planets where it rains rubies and sapphires. Planets with atmospheres made of vaporized rock. Planets where the surface is an ocean of lava hundreds of miles deep. Planets orbiting binary stars, where two suns rise and set in the alien sky. Planets orbiting pulsars, bathed in lethal radiation from the corpse of a dead star. Planets that don't orbit stars at all, rogue worlds cast out from their home systems, wandering the galaxy in eternal darkness. And every single one of these discoveries forces us to confront an uncomfortable truth. Our solar system, with its orderly planets in circular orbits, with its rocky worlds close to the sun and gas giants farther out, with its relative stability and lack of extreme phenomena, is not normal. We're not the template. We're the exception. For centuries, we assumed that other planetary systems would look like ours. We assumed that Jupiter-sized planets would orbit at Jupiter-like distances. We assumed that rocky planets would be close to their stars and gas giants would be far away. We assumed wrong. The universe doesn't care about our assumptions. The universe doesn't care about our models. The universe does what physics allows, and physics allows things we never imagined. HD 189733b exists because gravity, pressure, temperature, and time conspired to create it. There's no intent, no design, no purpose. It's simply what happens when you take a gas giant, place it next to a star, and wait. The laws of physics play out with cold indifference, creating a world of glass rain and hypersonic winds not because such a world serves a purpose, but because nothing in the laws of physics forbids it. And this is where the story gets personal for me. Because HD 189733b isn't just a curiosity, isn't just a bizarre footnote in the catalog of exoplanets. It's a laboratory. It's a place where we can test our understanding of atmospheric physics under conditions we could never recreate on Earth. It's a place where chemistry operates at extremes that push our models to the breaking point. Every observation of this planet, every spectrum we capture, every temperature map we construct, tells us something about how matter behaves under conditions of extreme heat and pressure. And that knowledge, that understanding, feeds back into our models of how planets form, how atmospheres evolve, how solar systems organize themselves. We learn about Earth by studying worlds that are nothing like Earth. We understand our home by exploring the alien. Let's talk about how we study a planet that's 63 light-years away. Because it's one thing to say we know HD 189733b has glass rain and hypersonic winds. It's another thing entirely to explain how we know this. How do you measure wind speed on a planet you can't even see directly? The answer is spectroscopy, and it's one of the most powerful tools in all of astronomy. When light passes through a gas, atoms absorb specific wavelengths, creating dark lines in the spectrum. Different elements absorb different wavelengths. Hydrogen absorbs certain colors. Sodium absorbs others. Methane, carbon monoxide, water vapor, each leaves its own fingerprint in the light. When we observe HD 189733b passing in front of its star, a tiny fraction of the star's light passes through the planet's atmosphere before reaching us. And in that light, we can see the absorption lines of whatever molecules exist in the upper atmosphere. But here's the clever part. If those molecules are moving, if there are winds, the absorption lines shift. Move toward us, the lines shift to shorter wavelengths. Move away, they shift to longer wavelengths. This is the Doppler effect, the same phenomenon that makes an ambulance siren change pitch as it passes you. By measuring these shifts, by analyzing how absorption lines change as the planet moves, we can calculate wind speeds. We can map the atmospheric circulation. We can watch weather systems evolve in real time, even though the planet itself is nothing more than a tiny point of light in even the most powerful telescopes. And it gets better. When the planet passes behind its star, blocked from our view, we can measure how much light the system loses. That tells us how much light the planet itself emits. Subtract the reflected starlight and what's left is thermal emission, the infrared glow of the planet's own heat. By measuring this at different wavelengths, we can construct a temperature map, determining which parts of the planet are hottest, where the heat is distributed, how efficiently the atmosphere transports energy from day to night. This is science at its finest. We can't send probes to HD 189733b. We can't sample its atmosphere directly. We can't measure its winds with anemometers or map its temperature with thermometers. All we have is light. Photons that left that planet 63 years ago, traveled through the void at the speed of light, and arrived at our telescopes carrying information encoded in their wavelengths and intensities. And from those photons, from those tiny messengers, we reconstruct an entire world. But observation is only half the story. The other half is theory, models, simulations that try to explain what we see. And this is where HD 189733b becomes truly fascinating from a theoretical perspective, because it pushes our models to the absolute limit. To simulate the atmosphere of a planet like this, you need to solve the equations of fluid dynamics, thermodynamics, radiative transfer, and chemistry simultaneously. You need to account for how heat is absorbed and emitted. How pressure and temperature affect wind patterns. How molecules form and break apart. How magnetic fields interact with charged particles. And you need to do this in 3 dimensions, at high resolution, over long time periods, capturing the full complexity of a dynamic atmosphere. The computational power required is staggering. We're talking about supercomputers running for weeks or months, performing trillions of calculations, just to simulate a few days of weather on an alien planet. And even then, the models are simplified. We make assumptions. We ignore small-scale turbulence. We approximate chemical reaction rates. We use averages where we should use distributions. And yet, despite these limitations, the models work. They predict hypersonic winds. They predict temperature offsets. They predict the formation of silicate clouds and the circulation patterns we observe. Not perfectly, but well enough to give us confidence that we understand the basic physics. Well enough to make predictions we can test with future observations. This is the scientific method in action. Observation inspires theory. Theory makes predictions. We observe again to test those predictions. And the cycle continues, each iteration bringing us closer to understanding. It's messy. It's uncertain. It's filled with false starts and contradictions. But it works. It works better than any other method humanity has ever devised for understanding the natural world. Now, let's zoom out for a moment and put HD 189733b in context. This planet orbits a star that's slightly cooler and smaller than our Sun, a K-type orange dwarf. These stars are incredibly common, making up about 12% of all stars in the galaxy. That means there are tens of billions of stars like HD 189733's parent star in the Milky Way alone. And if even a small fraction of them have planets like this, we're talking about billions of hot Jupiters, billions of worlds with glass rain and hypersonic winds, scattered throughout the galaxy. But here's the question that should haunt you. If hot Jupiters are common, and if they form through planetary migration, what happens to any smaller, rocky planets that were already there? What happens to potential Earths when a gas giant goes on a rampage through the inner solar system? The answer is grim. They get ejected. They get consumed. They spiral into the star. The migration of a hot Jupiter is an extinction event for any planets in its path. If Jupiter had migrated inward in our solar system, Earth wouldn't exist. Mars wouldn't exist. Venus and Mercury would have been cast into interstellar space or incinerated in the Sun. The solar system as we know it would be unrecognizable. This has profound implications for the search for life. Because if hot Jupiters are common, and if their formation requires planetary migration, then stable solar systems like ours might be rare. Really rare. The conditions necessary for life, at least life as we understand it, might require not just a planet in the habitable zone, but a planetary system that avoided the chaos of giant planet migration. We might be the lucky ones. We might inhabit a solar system that escaped the carnage. Or maybe not. Maybe hot Jupiters are evolutionary dead ends, systems that experienced catastrophic migration and are now sterile, devoid of the stable conditions necessary for life. Maybe the galaxy is filled with quieter systems, systems where planets formed and stayed put, where rocky worlds orbit in stable configurations, where life has time to emerge and evolve without being obliterated by rampaging gas giants. We don't know. We can't know, not yet. Our sample size is still too small, our observations still too limited. But every exoplanet we discover, every weird world like HD 189733b, helps us understand the statistics of planetary formation. Helps us determine what's common and what's rare. Helps us estimate how many habitable worlds might exist in the galaxy. And speaking of habitability, let's address the obvious question. Could there be life on HD 189733b? Short answer, no. Absolutely not. This is a world where anything resembling life as we know it would be instantly destroyed. The temperatures are too high. The pressures are too extreme. The radiation is too intense. There's no solid surface, no stable environment, no chemical pathways that could support the complex molecules necessary for biology. But, and this is a big but, HD 189733b might have had moons when it formed. And those moons, if they existed, would have been interesting. Potentially habitable, even. Before the planet migrated inward, when it orbited farther from its star, any large moons could have had liquid water, stable surfaces, protective atmospheres. They could have been worlds where life had a chance. But then the migration happened. The planet spiraled inward, and those moons would have been doomed. Stripped away by tidal forces. Crashed into the planet. Ejected from the system. Or, perhaps worst of all, dragged along for the ride, slowly heated and irradiated until their atmospheres boiled away and their surfaces became molten hellscapes. If life existed on those moons, it's gone now. Extinct. Erased by the indifferent cruelty of orbital mechanics. This is speculative, of course. We have no evidence that HD 189733b ever had moons. We have no evidence that those moons, if they existed, were habitable. But the scenario is plausible. Possible. And it serves as a reminder that habitability is fragile. Planetary systems are dynamic. Things change. And sometimes, those changes are catastrophic. Let me tell you about one of the most recent discoveries about HD 189733b, something that fundamentally changed how we think about this planet. In 2012, astronomers using the Hubble Space Telescope observed the planet during a stellar flare, an eruption on the star's surface that released enormous amounts of X-ray and ultraviolet radiation. What they saw was extraordinary. The planet's atmosphere responded almost immediately. Within minutes, the upper atmosphere heated up, expanded, and the rate of atmospheric escape increased by orders of magnitude. For a brief period, the planet was losing atmosphere at a rate of more than 100,000 tons per second. The flare lasted only a few hours, but in that time, the planet shed enough gas to fill Earth's oceans several times over. This was the first time, the very first time, that we had watched a stellar flare impact an exoplanet in real time. And it revealed something crucial. These planets don't just orbit their stars. They interact with them. The star's magnetic field, its stellar wind, its flares and coronal mass ejections, all of these affect the planet's atmosphere, its magnetic field, its long-term evolution. HD 189733b orbits so close to its star that it's essentially embedded in the star's outer atmosphere. It's not separate from its star. It's connected to it, linked by magnetic field lines, by flows of charged particles, by tides that distort both the planet and the star. The planet is being battered by stellar radiation every second of every day, and occasionally, during flares, that battery intensifies to levels that would sterilize Earth in minutes. And here's the kicker. The planet has a magnetic field. We know this because we've detected radio emissions, created by charged particles spiraling along magnetic field lines. This magnetic field is probably generated the same way Earth's is, by the motion of conducting fluid deep in the planet's interior. In Earth's case, that's liquid iron in the core. In HD 189733b's case, it's liquid metallic hydrogen. But unlike Earth, where our magnetic field protects us from solar radiation, HD 189733b's magnetic field isn't strong enough. It can't shield the atmosphere from the star's onslaught. It might slow the rate of atmospheric loss slightly, but it can't stop it. The planet is slowly but inevitably being stripped bare by its star, and there's nothing it can do about it. This is cosmic violence on a scale that's hard to fathom. Every stellar flare is an attack. Every burst of X-rays is a bombardment. And the planet, despite having a magnetic field, despite having an atmosphere that extends tens of thousands of miles into space, is losing the fight. Not quickly, but inexorably. Physics is patient. Time is on the star's side. Now let's talk about something that might seem trivial but is actually profound. HD 189733b transits its star. From our perspective on Earth, it passes directly in front of the star, blocking a tiny fraction of the star's light. This is how we discovered the planet in the first place. This is how we measure its size, its orbital period, its atmospheric composition. The transit method is responsible for finding thousands of exoplanets, including most of the planets we know about. But here's the thing. For a planet to transit from our perspective, the orbital plane has to be aligned almost perfectly with our line of sight. If the orbit is tilted even slightly, the planet misses the star's disk, and we see nothing. The probability of this alignment is roughly the star's diameter divided by the orbital diameter. For HD 189733b, that probability is about 20%. Not terrible odds, but not great either. Which means that for every hot Jupiter we detect through transits, there are probably 4 or 5 more that we're missing because their orbits aren't aligned correctly. And that means hot Jupiters are even more common than the raw numbers suggest. Extrapolate from the planets we can see to estimate how many exist in total, and you get numbers that are staggering. There could be billions of hot Jupiters in the Milky Way. Billions of worlds like HD 189733b, each one a laboratory of extreme physics, each one a testament to the diversity of planetary systems. And we're just scratching the surface. The planets we found so far are biased toward big planets orbiting close to their stars, because those are the easiest to detect. Small planets, planets in wide orbits, planets around dim stars, these are much harder to find. As our technology improves, as our telescopes get more sensitive, we're finding smaller and smaller planets. Planets the size of Neptune. Planets the size of Earth. Planets in their star's habitable zone, where liquid water could exist on the surface. HD 189733b is the extreme. It's the outlier. It's the planet that makes us question our assumptions and rethink our models. But it's not the goal. The goal is to find planets like Earth. Planets where life could exist. Planets where, maybe, life does exist. And every weird world we study, every hot Jupiter and lava planet and ice giant, brings us one step closer to understanding how planetary systems work, what conditions are necessary for habitability, and how rare or common Earth-like worlds might be. Let me share something that gives me chills every time I think about it. In 2015, astronomers used the Hubble Space Telescope to measure the color of HD 189733b directly. Not by inference, not through models, but by actual observation. They measured the light reflected by the planet during transit and compared it to the light from the star. And they determined that the planet is blue. Deep blue. Almost the same color as Earth when seen from space. But there the similarity ends. Earth is blue because of oceans. Because liquid water covers 70% of our planet's surface, and water absorbs red light and reflects blue. HD 189733b is blue because of glass. Because silicate particles scatter blue light while absorbing red. One planet is blue because of life. The other is blue because of annihilation. Same color. Opposite causes. This is why we need to be careful when we look at exoplanets. Color alone tells us nothing about habitability. A blue planet isn't necessarily an ocean world. A red planet isn't necessarily a desert. We need spectra. We need to analyze the light in detail, breaking it down into component wavelengths, identifying the specific molecules responsible for each absorption feature. Only then can we distinguish between a living world and a dead one. And that's what the James Webb Space Telescope is doing right now. Launched in 2021, Webb is the most powerful infrared telescope ever built, specifically designed to study exoplanet atmospheres. It can detect molecules that Hubble can't. It can measure temperature profiles with unprecedented precision. It can find biosignatures, chemical signatures that might indicate the presence of life. Webb has already observed HD 189733b, and the data is extraordinary. The spectrum shows water vapor, carbon monoxide, and carbon dioxide in abundances that match our models. But it also shows something unexpected. There are features in the spectrum that we can't fully explain, absorption lines that don't correspond to any molecule we predicted. This could be evidence of exotic chemistry, molecules forming under conditions so extreme that we've never encountered them in laboratories. Or it could be something else, some phenomenon we haven't considered, some physics we don't understand. This is the frontier. This is where science happens. Not in the confirmation of what we already know, but in the confrontation with the unexpected. HD 189733b is teaching us that the universe is stranger than we imagined. Stranger than we can imagine. And every observation raises new questions, opens new avenues of investigation, pushes us further into the unknown. But let's bring this back to Earth for a moment. Why should you care about a planet 63 light-years away? Why should you care about glass rain and hypersonic winds on a world you'll never visit, a world that would kill you instantly if you somehow got there? Because HD 189733b is a mirror. Not a literal mirror, but a conceptual one. It shows us what Earth could have been. If Jupiter had migrated inward. If the early solar system had been slightly more chaotic. If gravitational interactions had played out differently, Earth might not exist. We might not exist. And in place of our blue marble, our oasis in space, there might be another hot Jupiter, another world of glass and fire, orbiting where Earth does now. We are the product of chance. Not divine intervention, not cosmic purpose, but chance. The roll of gravitational dice. The outcome of chaotic orbital interactions that happened 4.5 billion years ago. We won the lottery. We got a stable solar system, a planet in the habitable zone, conditions that allowed life to emerge and evolve and eventually produce beings capable of wondering about their place in the universe. HD 189733b didn't win that lottery. It got the opposite. It got hell. But its existence, its very impossibility, tells us that the universe is vast and varied enough to produce both outcomes. It tells us that Earth-like worlds are probably rare, but they exist. Somewhere out there, among the hundreds of billions of stars in the galaxy, there are planets like ours. Planets with blue skies because of oceans, not glass. Planets with weather that doesn't kill. Planets where life has a chance. And maybe, just maybe, on one of those planets, there are beings looking up at their night sky, studying a star 63 light-years away, discovering a planet orbiting that star, a planet that seems impossibly fragile and perfect, a planet where the atmosphere is thin enough to be transparent, where water exists in liquid form, where the temperature is stable enough for complex chemistry. A planet called Earth. This is the perspective that HD 189733b gives us. We are not the center of the universe. We are not the template. We are one outcome among countless others, one roll of the dice that happen to come up in our favor. And recognizing this, acknowledging our cosmic insignificance while simultaneously marveling at our cosmic luck, is perhaps the most profound realization that science can offer. Let me take you deeper into the physics, because there's something about HD 189733b that we haven't fully addressed yet. How does a planet generate hypersonic winds? What's the mechanism that accelerates gas to 4,500 miles per hour? The answer lies in the day-night temperature difference. On Earth, temperature differences of 50 degrees are enough to create our weather. But the gradient on HD 189733b is 15 times larger. That means the potential energy available to drive circulation is 200 times greater. And because the planet has no continents, no mountains, no surface features to slow the winds, that energy converts almost entirely into kinetic energy. Wind speed. But there's a limit. You can't accelerate wind indefinitely. Eventually, you run into the sound barrier. Sound is just pressure waves moving through a medium, and those waves travel at a speed determined by the temperature and composition of the gas. On Earth, at sea level, sound travels at about 760 miles per hour. On HD 189733b, where the temperature is much higher, sound travels faster, maybe 2,000 miles per hour. But the winds are going twice that fast. So what happens when wind exceeds the speed of sound? You get shock waves. Supersonic flow. The air molecules don't have time to get out of the way. They pile up, creating regions of extremely high pressure and temperature. These shock waves dissipate energy, creating turbulence, heating the gas, making the whole system even more chaotic. The atmosphere of HD 189733b isn't just windy. It's a continuous sonic boom, a planet-wide shock wave that never stops. And this has consequences for the chemistry. When molecules move through a shock wave, they gain energy. A lot of energy. Enough to break chemical bonds. Molecules that are stable at 2000 degrees might not be stable at 3000 degrees. So as gas flows from the night side to the day side, passing through shock waves, molecules break apart. And as that gas cools on the night side, they reform. But not necessarily into the same molecules. You might start with carbon dioxide on the night side, break it apart in the shock, and reform it as carbon monoxide on the day side. The planet's chemistry is being constantly reset, driven not just by temperature but by shock heating. This is chemistry under extreme conditions, and it's something we can't fully replicate in laboratories on Earth. We can create high pressures. We can create high temperatures. But we can't create the combination of pressures, temperatures, and hypersonic flows that exist on HD 189733b. So every observation of this planet, every spectrum we take, every measurement we make, is a laboratory experiment being conducted on a planetary scale. Now, let's talk about the star's effect on the planet. HD 189733's parent star is magnetically active. It has star spots, like sunspots but larger. It has flares that release more energy than 1 billion nuclear bombs. And because the planet orbits so close, it's in the line of fire. Every flare hits the planet directly. Every coronal mass ejection slams into the planet's magnetosphere. When a flare hits, the planet's upper atmosphere heats up rapidly. The gas expands. The scale height, the vertical distance over which pressure drops by a factor of E, increases dramatically. And because the atmosphere is now more extended, it intercepts more of the star's light. This creates a feedback loop. More heating leads to more expansion, which leads to more heating, which leads to more expansion. Eventually, the atmosphere reaches a point where gas at the top is moving faster than the escape velocity. It's no longer bound to the planet. It streams away into space, never to return. This process, called hydrodynamic escape, is how HD 189733b is losing its atmosphere. It's not a steady drip. It's episodic. Most of the time, the loss rate is relatively modest, maybe a few tons per second. But during flares, it spikes to thousands of tons per second. And over billions of years, those spikes add up. The planet has probably lost several percent of its total mass this way. Maybe more. But here's what's fascinating. Despite this constant bombardment, despite billions of years of atmospheric erosion, HD 189733b still has a thick atmosphere. It still has clouds. It still has weather. The reason is gravity. The planet is massive enough that even though gas is escaping from the top of the atmosphere, the bulk of the atmosphere remains bound. It's like trying to boil away the ocean. You can evaporate water from the surface, but the ocean itself isn't going anywhere anytime soon. This is a crucial concept for understanding habitability. A planet needs to be massive enough to hold on to its atmosphere, but not so massive that it becomes a gas giant. Earth sits in the sweet spot. We're big enough to retain our atmosphere over billions of years, but small enough that we have a solid surface, that plate tectonics can operate, that life can emerge. HD 189733b is too massive. It's a gas giant. But somewhere between Earth and HD 189733b, there's a transition. A size where planets start to accumulate thick hydrogen atmospheres, where they become mini-Neptunes rather than super-Earths. We've found planets in this transition zone. Planets 10 times Earth's mass with thick atmospheres but potentially rocky cores beneath. Are these planets habitable? Can life exist under hundreds of bars of hydrogen pressure? We don't know. But these are the questions that HD 189733b is helping us frame. Every extreme world we study expands our understanding of what's possible, what conditions can exist, what environments might support life. And life is the ultimate question, isn't it? We study exoplanets not just for the sake of cataloging them, not just to satisfy academic curiosity, but because we want to know if we're alone. We want to know if life is common or rare. We want to know if intelligence, consciousness, civilization, are inevitable outcomes of cosmic evolution or flukes, accidents that happen once in a galaxy and never repeat. HD 189733b can't answer that question directly. But it contributes to the answer by helping us understand planetary systems, by showing us that planets come in varieties we never imagined, by demonstrating that the universe is far more creative than our limited experience might suggest. Every planet we discover, every weird world we characterize, refines our estimates of how many habitable worlds exist. And those estimates guide our search, help us decide where to point our telescopes, which stars to study, which planets to investigate in detail. Let's talk numbers. There are roughly 400 billion stars in the Milky Way. Recent surveys suggest that, on average, each star has at least one planet. That's 400 billion planets, minimum. Of those, maybe 10% are in their star's habitable zone. That's 40 billion potentially habitable worlds. But not all of those will be Earth-like. Some will be too big. Some will be too small. Some will have the wrong atmosphere. Some will orbit stars that are too active, too prone to flares. Some will have had their atmospheres stripped by migrating hot Jupiters. Let's be pessimistic. Let's say only 1% of those 40 billion potentially habitable worlds are actually habitable. That's still 400 million Earth-like planets in our galaxy alone. 400 million worlds where life could exist. And if even 1% of those actually have life, that's 4 million living worlds. And if even 1% of those have intelligent life, that's 40,000 civilizations. These are wild guesses, of course. We don't know the actual numbers. But the point is, even with conservative estimates, even being pessimistic at every step, we end up with thousands of potential civilizations in the galaxy. And if we're wrong, if habitable worlds are more common than we think, if life emerges more easily than we assume, the numbers could be much higher. But here's the paradox. If there are thousands of civilizations in the galaxy, where are they? Why haven't we detected their signals? Why haven't they visited us? This is the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" HD 189733b doesn't answer this question, but it illuminates it. Because for every habitable world, there are probably dozens of uninhabitable ones. For every stable planetary system, there are probably several chaotic ones destroyed by migrating gas giants. The universe is dangerous. Planetary systems are fragile. Life, even if it emerges, faces constant threats from asteroid impacts, supernovae, gamma-ray bursts, stellar flares, climate instability. The universe is not conducive to life. It's hostile. And surviving long enough to develop technology, to build civilization, to reach for the stars, requires not just intelligence but luck. A lot of luck. Maybe the reason we haven't found evidence of other civilizations is that civilizations are rare. Not because planets are rare, but because the specific combination of circumstances necessary for intelligent life to emerge and survive is rare. Or maybe civilizations exist but don't last. Maybe the transition from planetary species to spacefaring species is a bottleneck, a filter that most civilizations don't pass through. Maybe we're early. Maybe we're late. Maybe we're alone. We don't know. But every planet we study, every system we characterize, every data point we collect, brings us closer to answering these questions. HD 189733b is one data point among thousands. But it's an important one. It shows us what happens when planetary migration goes wrong. It shows us the limits of atmospheric stability. It shows us that planets can exist in conditions we thought were impossible. And all of that information feeds into our models, our estimates, our understanding of the cosmos. Now let's discuss the future. What comes next for HD 189733b research? We've studied this planet intensively for almost 2 decades, but there's still so much we don't know. We don't know if it has a ring system. We don't know if it has any surviving moons. We don't know the exact composition of its core. We don't know how its magnetic field interacts with the stellar wind. We don't know if there are seasons, if the atmospheric circulation changes over time, if there are long-term trends in temperature or cloud cover. These questions require new observations, better instruments, longer baselines. The James Webb Space Telescope will help. So will the next generation of ground-based telescopes, massive instruments with mirrors 30 meters or more in diameter, capable of collecting more light, resolving finer details, detecting fainter signals. And eventually, we'll build space telescopes specifically designed to image exoplanets directly, blocking out the star's light and capturing photons reflected by the planet itself. When that happens, we'll be able to see HD 189733b not as a point of light, not as a spectrum, but as an actual image. A tiny blue dot, separated from its star, proof that we can resolve these distant worlds. But imaging is just the beginning. The ultimate goal is spectroscopy of Earth-like planets. Finding biosignatures. Detecting oxygen, ozone, methane in combinations that can only be explained by life. HD 189733b is too hot, too hostile, for life. But the techniques we're developing to study it, the methods we're refining, the models we're building, all of this applies to other planets. Cooler planets. Smaller planets. Planets in habitable zones. And when we finally detect a biosignature, when we find compelling evidence of life on another world, it will be the culmination of decades of work studying planets like HD 189733b. Because you can't understand the normal without studying the extreme. You can't calibrate your instruments, validate your models, or trust your interpretations unless you've tested them against planets where the physics is unambiguous, where the conditions are so extreme that there's no room for error. HD 189733b is our test case. It's the planet where we learned how to do exoplanet science. And the lessons we've learned will guide us as we search for life among the stars. Let me tell you about one more aspect of this planet that I find deeply moving. HD 189733b is visible from Earth. Not with the naked eye, you'd need a telescope for that, but it's there. Right now, as you're reading this, light from that planet is traveling through space at 186,000 miles per second. In about 63 years, give or take, that light will arrive at Earth. Someone will point a telescope at that distant star, and they'll see what the planet looks like today. Think about that. The planet exists not just in space but in time. What we see when we observe HD 189733b is history. We're seeing the planet as it was in 1962. The planet has moved on. It's orbited its star more than 10 million times since the light we're seeing today left its atmosphere. The weather has changed. Storms have formed and dissolved. Atmospheric gases have escaped and been replaced. We're seeing a ghost, an echo of a world that no longer exists in the exact form we observe. And this is true for all astronomical observations. The universe is so vast, light so slow, that everything we see is history. The sun as it was 8 minutes ago. The nearest star as it was 4 years ago. The Andromeda Galaxy as it was 2.5 million years ago. The cosmic microwave background as it was 13.8 billion years ago. Astronomy is the study of history. We're archaeologists of light, piecing together the story of the universe from photons that have traveled unimaginable distances to reach us. HD 189733b's light carries information. Information about temperatures, pressures, chemical compositions, wind speeds. Information encoded in wavelengths and intensities, in absorption lines and emission features. And we extract that information using instruments and mathematics, transforming light into knowledge, photons into understanding. This is the miracle of modern science. We can study a world we'll never touch using nothing but light. But there's a philosophical dimension to this as well. HD 189733b exists whether we observe it or not. Its winds blow, its atmosphere churns, its magnetic field deflects charged particles, all without any audience, without any purpose, without any significance beyond the physical processes that create it. The planet doesn't care that we're watching. It doesn't care that we find it fascinating. It just is. And yet, by observing it, by studying it, by trying to understand it, we imbue it with meaning. We make it part of our story, part of humanity's quest to understand the cosmos. We take a meaningless collection of gas and heat and pressure and transform it into knowledge, into science, into something that enriches our species, that expands our horizons, that reminds us of our place in the universe. This is what science does. It takes the indifferent universe and finds patterns, discovers laws, creates understanding. It doesn't change the universe, but it changes us. It transforms us from ignorant apes wondering about lights in the sky to a species capable of comprehending the workings of distant worlds. And in that transformation, we find meaning. Not given to us by the universe, but created by us through the act of understanding. HD 189733b is just one planet among billions. But it's our planet now, in the sense that we've claimed it for science, that we've made it part of our intellectual heritage, that future generations will study what we've learned and build upon it. 63 light-years might seem like an unbridgeable distance, but knowledge transcends distance. Understanding transcends time. We are connected to that distant world through the light that reaches us, through the equations that describe it, through the curiosity that drives us to look up and wonder. As we conclude this journey through the strangest planet NASA has ever found, I want you to hold on to one thought. HD 189733b is real. It's not a fantasy. It's not speculation. It's not a what-if scenario dreamed up by science fiction writers. It's a world that exists, right now, this very moment, orbiting a star in the constellation Vulpecula. The glass is falling. The winds are screaming. The atmosphere is bleeding into space. And none of it knows we're watching. But we are watching. With telescopes and spectrographs, with satellites and supercomputers, with curiosity and determination, we're watching. We're learning. We're understanding. And in doing so, we're doing what humans do best. We're exploring. Not with ships and spacesuits, not yet, but with light and mathematics, with observation and theory, with the most powerful tool ever created, the scientific method. HD 189733b challenges us. It forces us to confront the limits of our intuition, to recognize that the universe doesn't conform to our expectations. It reminds us that we live in a cosmos far stranger, far more diverse, far more magnificent than we ever imagined. And it invites us to keep looking, keep searching, keep pushing the boundaries of knowledge further into the unknown. Because somewhere out there, among the hundreds of billions of stars, there are planets even stranger than HD 189733b. Planets we haven't found yet. Planets that will force us to rewrite textbooks, revise theories, expand our understanding even further. And beyond those strange worlds, there might be ordinary worlds. Worlds with oceans and continents. Worlds with blue skies because of water, not glass. Worlds where life has taken hold, where evolution has played out across billions of years, where beings capable of wonder look up at their night sky and ask the same questions we ask. Are we alone? What's out there? What does it mean? HD 189733b doesn't answer these questions. But it reminds us why they matter. It reminds us that the universe is vast beyond comprehension, that exploration is essential to being human, that curiosity is perhaps our species' greatest trait. And it reminds us that science, for all its limitations, for all its uncertainties, is the best method we have for transforming wonder into knowledge. So the next time you look up at the night sky, remember that blue dot orbiting an orange star 63 light-years away. Remember the glass rain and the hypersonic winds. Remember that we live in a universe capable of creating such impossibility, such extremes, such utterly alien environments. And remember that we, improbable beings on an improbable planet, have somehow developed the ability to study these distant worlds, to understand them, to make them part of our story. That's not just science. That's transcendence. That's humanity at its best, reaching beyond ourselves, beyond our planet, beyond our solar system, to touch the infinite. HD 189733b is strange, yes. But the strangest thing of all might be that we, collections of atoms formed in the hearts of ancient stars, are capable of understanding it. And that understanding, hard-won through observation and calculation, through trial and error, through generations of scientists building upon each other's work, is perhaps the most beautiful thing our species has ever achieved. We are stardust contemplating stardust. We are the universe awakening to itself. And HD 189733b, that blue nightmare world of glass and fire, is part of that awakening. Part of our cosmic coming of age. Part of the never-ending journey to understand everything. The search continues. The universe awaits. And somewhere, 63 light-years away, a planet we'll never visit continues its endless race around an alien sun, indifferent to our observation, unconcerned with our fascination, existing simply because physics allows it. And that's enough. That's everything. Let's dive deeper into what makes HD 189733b not just strange, but scientifically revolutionary. Because here's something most people don't realize: this planet has changed how we think about planetary interiors. When you compress hydrogen hard enough, something remarkable happens. The electrons get squeezed out of their atomic orbitals. They become free to move, creating a metallic state where hydrogen conducts electricity like copper or aluminum. This isn't theoretical anymore. We've created metallic hydrogen in laboratories for microseconds at pressures exceeding 4 million atmospheres. But in the core of HD 189733b, this exotic state of matter exists in quantities measured not in milligrams but in Earth masses. Imagine an ocean of liquid metal hydrogen thousands of miles deep. It flows. It convects. Heat from the planetary core rises through it, creating currents that dwarf anything in Earth's oceans. And as this conducting fluid moves through the planet's magnetic field, it generates electric currents measured in billions of amperes. These currents, in turn, reinforce the magnetic field, creating a dynamo that's been running continuously for billions of years. The magnetic field strength at the planet's cloud tops is probably several hundred times stronger than Earth's. Strong enough to channel charged particles from the stellar wind into concentrated beams that slam into the polar regions. Strong enough to create auroras that would dwarf anything we see on Earth or Jupiter. These auroras pump gigawatts of energy into the upper atmosphere, creating hotspots at the poles that might rival the temperature of the day side. But here's where it gets truly weird. The planet's rapid rotation, completing a spin in just 53 hours, combines with those hypersonic winds to create a phenomenon called differential rotation. Different layers of the atmosphere rotate at different speeds. The equator might complete a rotation in 50 hours while the mid-latitudes take 55. This shearing motion stores enormous amounts of energy that gets released in atmospheric storms. And I'm not talking about hurricanes here. Earth's hurricanes are powered by water evaporating from warm oceans, releasing latent heat as it condenses into clouds. They're heat engines converting thermal energy into rotational energy. HD 189733b's storms are fundamentally different. They're shear instabilities, vortices that form when adjacent layers of atmosphere slide past each other at different speeds. Think of them as atmospheric tornadoes, except they're the size of Earth and they last for years. We've detected these storms indirectly through variations in the planet's brightness. As a massive vortex rotates into view, it changes the amount of starlight the planet reflects. These variations repeat on timescales of days to weeks, suggesting that some storm systems are semi-permanent features, persisting despite the chaotic atmospheric conditions. The mathematics of fluid dynamics on HD 189733b is mind-bending. On Earth, we use something called the Rossby number to characterize atmospheric flow. It's the ratio of inertial forces to Coriolis forces, essentially measuring how much rotation affects wind patterns. For Earth's atmosphere, the Rossby number is around 0.1. For HD 189733b, it's closer to 10. That means rotation is almost irrelevant. The winds are so fast that the planet's spin becomes a minor perturbation rather than the dominant organizing force. This breaks all our intuition about how weather should work. On Earth, rotation creates organized patterns, high-pressure systems, low-pressure systems, jet streams that meander around the globe. But on HD 189733b, the flow is dominated by that day-night temperature gradient. The winds don't curve gracefully around pressure systems. They blast directly from the hot side to the cold side with barely any deflection. It's atmospheric flow in a regime we never encounter on Earth, governed by equations that have solutions we're only beginning to understand. Let me tell you about the planet's thermal tide. On Earth, we have ocean tides caused by the moon's gravity. The water rises and falls twice a day as Earth rotates beneath the moon. HD 189733b has atmospheric tides caused by stellar heating. As the planet orbits, the star's heat creates a bulge in the atmosphere on the day side. But the atmosphere can't respond instantaneously. There's a lag. By the time the atmosphere heats up and expands, the planet has moved in its orbit. The bulge ends up offset from the subsolar point, creating an asymmetric distribution of mass. And here's the crucial part, this asymmetric mass distribution creates a torque. The star's gravity pulls on the atmospheric bulge, trying to drag the planet's rotation into synchronization with its orbit. Over billions of years, this torque is what locked the planet's rotation to its orbital period. The same process locked our moon's rotation to its orbit around Earth. But for HD 189733b, the tidal forces are millions of times stronger because it orbits so close to its star. The energy dissipated by these tides is staggering. As the solid interior of the planet tries to rotate slightly faster or slower than the atmosphere, friction generates heat. Enormous amounts of heat. We're talking about terawatts of power continuously converted from rotational energy into thermal energy. This tidal heating might contribute significantly to the planet's internal temperature, keeping the interior molten, maintaining convection, sustaining the magnetic field dynamo. But tidal forces don't just heat the planet. They deform it. The difference between the star's gravitational pull on the near side versus the far side creates a tidal bulge, stretching the planet into a slightly ellipsoidal shape. For a planet as close as HD 189733b, this deformation is substantial. The planet might be several hundred miles taller along the star-planet axis than along the perpendicular direction. It's being constantly squeezed and stretched by gravity, like a stress ball in the hands of a cosmic giant. This deformation affects everything. The atmospheric pressure distribution changes. The gravitational field becomes non-uniform. And most importantly, the process dissipates energy, heating the planet from the inside out. Jupiter's moon Io experiences the same phenomenon, though powered by Jupiter rather than a star. The result is the most volcanically active body in the solar system, with hundreds of active volcanoes spewing sulfur compounds into space. HD 189733b doesn't have volcanoes because it doesn't have a solid surface, but the principle is the same. Tidal forces pump energy into the planet, maintaining it in a state of permanent geological, or rather atmospherological, activity. Now let's address something that's been puzzling astronomers since the planet's discovery: its mass. HD 189733b has a mass about 0.13 times that of Jupiter. That's slightly more than Jupiter but not dramatically so. Yet its radius is about 1.138 times Jupiter's radius. That makes it less dense than Jupiter, which seems counterintuitive. More massive objects should be denser, right? Wrong. And this is where planetary science gets deliciously complicated. Jupiter-mass planets have a peculiar property: adding mass doesn't increase their radius proportionally. In fact, above a certain mass threshold, adding more mass actually makes the planet smaller. The increased gravity compresses the interior more efficiently, offsetting the additional volume. The most massive gas giants are actually slightly smaller than Jupiter. But HD 189733b is larger than Jupiter despite being only slightly more massive. Why? The answer is heat. The planet is receiving enormous amounts of stellar radiation, roughly 9,000 times what Jupiter receives from the Sun. This energy heats the atmosphere, causing it to expand. The planet puffs up like a hot air balloon, its radius inflated beyond what gravity alone would dictate. This is called radius inflation, and it's common among hot Jupiters. But the amount of inflation we observe on HD 189733b is more than models predict based on stellar heating alone. Even accounting for the intense irradiation, the planet is about 10% larger than it should be. Something else is heating the interior. That something is probably tidal dissipation. The energy from tidal deformation is deposited deep in the planet's interior, preventing the planet from contracting to its natural size. It's locked in a state of permanent thermal expansion, unable to cool, unable to contract, held open by forces both external and internal. This has profound implications for understanding planetary evolution. Planets aren't static. They change over time. They cool, contract, and eventually settle into equilibrium configurations. But hot Jupiters like HD 189733b never reach equilibrium. They're constantly being pumped with energy from their stars, constantly being deformed by tides, constantly losing mass through atmospheric escape. They exist in dynamic steady states, balancing energy input against energy loss, maintaining their inflated sizes through perpetual heating. The chemistry happening in this environment is equally extreme. On the day side, temperatures are high enough to dissociate most molecules. Water vapor breaks into hydrogen and oxygen. Methane breaks into carbon and hydrogen. Even carbon monoxide, one of the most stable molecules, starts to dissociate at these temperatures. You end up with a soup of atomic species: hydrogen, helium, carbon, oxygen, nitrogen, all floating around as individual atoms rather than bound in molecules. But as this gas flows to the night side and cools, molecules reform. Except they don't necessarily reform into the same molecules they started as. Chemical equilibrium shifts with temperature. At 3000 degrees, carbon prefers to bond with oxygen forming carbon monoxide. At 2000 degrees, it might prefer methane. The atmosphere is constantly rebalancing itself, creating a dynamic chemistry that never settles into equilibrium. And then there are trace species. Elements like sodium, potassium, and iron that exist in tiny amounts but leave huge signatures in the spectrum. These metals vaporize on the day side, creating a metallic vapor that absorbs certain wavelengths of light very efficiently. This is how we detected sodium in the planet's atmosphere, by observing the planet during transit and seeing sodium's characteristic absorption lines appear in the star's spectrum. But sodium does something else. It ionizes easily, losing an electron and becoming positively charged. These charged particles interact with the planet's magnetic field, getting swept up and accelerated. Some of them escape the planet entirely, creating an extended envelope of sodium atoms that surrounds the planet and trails behind it like a comet tail. We've detected this tail extending tens of thousands of miles from the planet, a ghostly stream of atoms being continuously replenished by evaporation from the lower atmosphere. This brings us to something truly remarkable about HD 189733b, we can watch its weather change in real time. By monitoring the planet continuously over many orbits, astronomers have observed variations in temperature, brightness, and atmospheric composition that occur on timescales of hours to days. These aren't measurement errors. They're real changes in the planet's atmospheric state. For instance, the hot spot offset, that 30-degree shift eastward of the hottest region from the subsolar point, isn't constant. It varies. Sometimes it's 25 degrees. Sometimes it's 35. These variations suggest that the atmospheric circulation isn't steady. The wind patterns change. Storm systems form and dissipate. The atmosphere breathes, fluctuating around an average state but never settling into perfect stability. Why does this matter? Because it tells us that the atmosphere is actively turbulent. The flow isn't laminar and smooth. It's chaotic, filled with eddies and vortices at all scales. Energy cascades from large-scale circulation down to small-scale turbulence and eventually dissipates as heat. This cascade is governed by the same physics that describes turbulence in Earth's atmosphere or in ocean currents, but operating at energy levels billions of times higher. Understanding turbulence on HD 189733b helps us understand turbulence everywhere. Because turbulence is one of the great unsolved problems in classical physics. We can write down the equations, the Navier-Stokes equations, that describe fluid flow. But we can't solve them analytically for turbulent flows. We have to use computers, running massive simulations that approximate the solutions. And every new regime we explore, every new set of conditions we test, improves those approximations and deepens our understanding. HD 189733b is a laboratory for studying turbulence in a regime completely inaccessible on Earth. The Reynolds number, a dimensionless quantity that characterizes the onset of turbulence, is astronomical on this planet. Literally astronomical. The flows are so violent, the scale so large, that turbulence exists in forms we've never encountered. And by observing how the planet's atmosphere behaves, by tracking those weather variations, we're learning about the fundamental nature of chaotic fluid dynamics. Let me tell you about a prediction that models made about HD 189733b, a prediction that was later confirmed by observations. Computer simulations suggested that the planet should have equatorial superrotation, a jet stream at the equator that moves faster than the planet rotates. This phenomenon exists on Venus, where winds in the upper atmosphere circle the planet in just 4 days even though Venus itself takes 243 days to rotate. On HD 189733b, the mechanism is different. The day-night heating drives winds from west to east along the equator, accelerating them to speeds that exceed the planet's rotational velocity. These winds form a coherent jet stream that circles the planet, transporting heat and maintaining that eastward offset of the hot spot. Observations confirm this. Spectroscopic measurements showed Doppler shifts indicating west to east motion at the velocities models predicted. This was a triumph for atmospheric physics. We predicted a phenomenon on an alien world using nothing but equations and computation. Then we observed that world and found exactly what we predicted. This is how science works at its best. Theory makes testable predictions, observations confirm or refute those predictions, and our understanding advances. But not everything about HD 189733b matches predictions. There are anomalies, discrepancies between models and observations that suggest we're missing something important. For instance, the planet appears to reflect more light than models suggest it should. The albedo, the fraction of incoming light that gets reflected, is higher than expected given the atmospheric composition and cloud properties we've inferred. What's going on? Nobody knows for sure. One possibility is that there are high-altitude hazes, layers of tiny particles suspended in the upper atmosphere that scatter light efficiently. These hazes might be composed of complex organic molecules, photochemical products created when ultraviolet light from the star breaks apart methane and other simple molecules. The fragments recombine into larger molecules, polymers that condense into haze particles. This chemistry, called photochemistry, is responsible for the orange haze on Saturn's moon Titan. Titan's atmosphere is mostly nitrogen with a few percent methane, but ultraviolet light creates an entire suite of complex organic molecules, building blocks that rain down onto the surface and create lakes and seas of liquid methane. HD 189733b is far too hot for liquid methane, but the same photochemical processes might create hazes in the upper atmosphere where temperatures are cooler. If these hazes exist, they have profound implications. They would affect the planet's energy balance, reflecting more starlight and reducing the amount of energy absorbed. They would affect atmospheric chemistry, providing surfaces where reactions can occur more efficiently than in the gas phase. And they would affect observations, creating spectral features that complicate our attempts to determine atmospheric composition. But hazes are hard to model. The chemistry is complex, involving hundreds of reactions between dozens of molecular species. The particles themselves evolve over time, growing through coagulation and settling under gravity. And the interaction between hazes and radiation requires solving radiative transfer equations that account for scattering, absorption, and emission at multiple wavelengths. It's computationally intensive work that pushes even modern supercomputers to their limits. Yet this is the work that must be done if we want to truly understand HD 189733b. Every layer of complexity we add to our models, every new process we include, brings us closer to capturing the full reality of this alien world. Science isn't about finding simple answers. It's about building accurate models that account for all the messy, complicated details that make nature what it is. And speaking of complicated, let's talk about the planet's gravitational influence on its star. You might think a planet, even a massive one, couldn't affect a star. But you'd be wrong. HD 189733b is massive enough and close enough that its gravity creates a measurable wobble in the star's position. As the planet orbits, the star orbits too, moving in a tiny circle around the system's center of mass. This wobble is how we detect many exoplanets. By measuring the star's velocity through spectroscopy, watching how its spectral lines shift back and forth due to the Doppler effect, we can infer the presence of an orbiting planet. For HD 189733b, the star's velocity variation is about 200 meters per second. That's roughly the speed of a commercial jet aircraft. We can measure this from 63 light-years away. Think about that level of precision. We're detecting motion equivalent to a jet plane's speed on a star located 600 trillion kilometers from Earth. But the planet does more than just make the star wobble. It also raises tides on the star itself. Just as the moon raises ocean tides on Earth, HD 189733b raises tides in the star's outer layers. The star's plasma bulges slightly toward the planet, creating a tidal distortion. And because the star rotates faster than the planet orbits, this bulge gets carried ahead of the planet, exerting a torque that gradually accelerates the planet's orbit. Over billions of years, this torque will cause the planet to spiral outward, moving to a slightly larger orbit. Simultaneously, the star's rotation slows down as angular momentum is transferred to the planet's orbit. Eventually, hundreds of millions of years from now, the system will reach a state where the star's rotation period equals the planet's orbital period. At that point, the tidal bulge will always point directly at the planet, the torque will vanish, and the system will be tidally locked in both directions. But that's far in the future. Right now, the system is evolving, changing, slowly but inexorably adjusting its configuration in response to tidal forces. And we can measure this evolution. By observing the system over many years, tracking tiny changes in orbital period or stellar rotation, we can test theories of tidal evolution and constrain parameters that govern how quickly these processes operate. Here's something that blew my mind when I first learned it: HD 189733b is detectable from Earth with amateur equipment. You don't need Hubble or Webb or a professional observatory. A good backyard telescope, a decent CCD camera, and some careful timing are enough to observe the planet transiting its star. You can measure the slight dimming that occurs when the planet passes in front of the star, detect the same phenomenon that professional astronomers study. This democratization of astronomy is extraordinary. For most of human history, studying the cosmos required access to expensive instruments at remote locations. Now, anyone with a few $1,000s and clear skies can contribute to exoplanet science. Amateur astronomers around the world monitor transiting planets, providing data that complements professional observations and helps track long-term changes. And there's something profound about this. HD 189733b isn't just abstract knowledge accessible only to specialists. It's a physical phenomenon that anyone can verify, can observe with their own equipment, can experience firsthand. This connection between professional science and public participation enriches both. Scientists get more data. The public gets a deeper appreciation for the scientific process. Everyone benefits. But let's zoom back out to the big picture. HD 189733b exists in a specific context, a planetary system that probably contains other planets we haven't detected yet. Most stars with planets have multiple planets, not just one. Our solar system has 8 planets plus numerous dwarf planets. The odds are good that HD 189733b has siblings, other worlds orbiting the same star at different distances. Why haven't we found them? Because they're harder to detect. HD 189733b is easy to spot, it's big, it's close to its star, and it transits. Smaller planets in wider orbits produce smaller signals that require longer observations and higher precision to detect. But those planets might be there, hidden in the data, waiting for better instruments or more clever analysis techniques to reveal them. If those planets exist, they've had an interesting history. Because HD 189733b didn't form where it is now. It migrated inward from the outer solar system. And that migration was violent. Any planets in its path would have been scattered, ejected, or consumed. The current architecture of the HD 189733 system is probably the result of catastrophic dynamical evolution that destroyed the original planetary configuration. Imagine what it must have been like in the early days of this system. A massive gas giant, newly formed, drifting slowly inward due to interactions with the protoplanetary disk. Ahead of it, smaller planets in nearly circular orbits, perhaps Earth-sized worlds in or near the habitable zone. The gas giant approaches. Gravitational interactions begin. Orbits become eccentric, unstable. Planets swing wildly through the inner system, colliding with each other, breaking apart, falling into the star. It's planetary apocalypse, chaos on a system-wide scale. And when the dust settled, metaphorically speaking, what remained was HD 189733b in its tight orbit, perhaps a few smaller planets in distant orbits that survived by luck, and a lot of debris, asteroids, comets, dust. The system we observe today is the survivor, the post-apocalyptic remnant of what was once probably a more diverse and complex planetary family. This narrative isn't unique to HD 189733. It's probably common. Most hot Jupiters likely formed far from their stars and migrated inward, disrupting whatever planetary systems existed before. Which means that hot Jupiter systems are graveyards. They're places where Earth-like planets probably existed but no longer do, destroyed by the same processes that created the hot Jupiters we observe. This has implications for estimating habitable planets. If 10% of stars host hot Jupiters, and if those hot Jupiters destroyed potential habitable planets during their migration, then 10% of stars have been essentially sterilized, rendered incapable of hosting complex life. That's a significant fraction. It reduces the number of habitable worlds in the galaxy and makes Earth even more precious than we thought. But here's the counterargument: hot Jupiter systems might create habitable worlds even as they destroy them. During the migration phase, collisions between planets could create debris disks. That debris could recoalesce into new planets, formed from the wreckage of the old ones. These second-generation planets would be different, enriched in heavy elements from the cores of destroyed worlds, but they might still be habitable. Life could emerge not on primordial planets but on phoenixes born from planetary destruction. We don't know if this happens. It's speculation based on theory. But it's plausible speculation, grounded in physics and orbital mechanics. And it's testable. As we find more planets and characterize their compositions, we might detect signatures of second-generation worlds, unusual element ratios, unexpected densities, chemical fingerprints that reveal violent pasts. HD 189733b itself tells us nothing about this directly. It's a lone giant in its inner system. Whatever story its formation and migration holds locked away in its composition and orbital elements. But it represents a class of planets that has reshaped our understanding of how planetary systems evolve. Every hot Jupiter we study adds another piece to the puzzle, another data point constraining models of planet formation and migration. Here's a question that keeps astronomers up at night: will HD 189733b survive? The planet is losing mass, its star is active and hostile, tidal forces are enormous. Could the planet eventually be completely destroyed, stripped down to just its core, or even that consumed by the star? The answer appears to be yes, but not anytime soon. Calculations suggest the planet is losing roughly 100,000 tons of material per second. That sounds like a lot, but the planet's total mass is about 2.5 times 10 to the 27th kilograms. At current loss rates, it would take roughly 1 trillion years to completely evaporate the planet. The star will die first, swelling into a red giant and likely consuming the planet in about 5 billion years. So HD 189733b is doomed, but its doom is measured in eons. On human timescales, on geological timescales, even on the timescales of stellar evolution, the planet is stable. It will be there, glass raining sideways, winds screaming at hypersonic speeds, atmosphere bleeding into space, for billions of years to come. Long after Earth becomes uninhabitable, long after the Sun exhausts its hydrogen fuel, HD 189733b will still be there, suffering its eternal torment under the relentless gaze of its star. There's something almost poetic about that. This world we've discovered, this nightmare planet of impossible extremes, will outlast us. It will outlast our civilization. It will outlast our species. When the last human has breathed their last breath, when Earth is a barren cinder circling a dying star, HD 189733b will still be there. Indifferent. Eternal. Enduring. And perhaps millions of years from now, when another intelligent species arises somewhere in the galaxy, they too will point their telescopes at that distant star. They too will discover that blue planet. They too will marvel at its impossibility. And maybe they'll wonder, as we do now, if anyone else out there is watching, if anyone else cares, if the universe even notices its own magnificence. The universe doesn't notice. But we do. And in that noticing, In that act of observation and understanding, we become the universe's consciousness. We become the means by which the cosmos comes to know itself. HD 189733b exists whether we observe it or not. But by observing it, we transform it from a mere physical object into something more, a testament to human curiosity, a symbol of our drive to explore, and a reminder that the universe is far stranger and more wonderful than we ever dared imagine. Let's talk about something that doesn't get enough attention: the sheer improbability of detecting HD 189733b in the first place. The planet's transit, that tiny dimming when it passes in front of its star, reduces the star's brightness by approximately 2.4%. That's like trying to detect the difference between a 100-watt light bulb and a 97.6-watt bulb from across a football field. At night, while someone's shaking the bulb, the precision required to make this measurement is absurd. We're talking about detecting brightness changes smaller than the variation caused by a single bird flying past the telescope. Smaller than the flicker caused by atmospheric turbulence. Smaller than the noise in the detector's electronics. Yet we do it routinely. We've gotten so good at this that we can now detect planets smaller than Earth causing brightness changes of 0.01% or less. The technology that makes this possible didn't exist 30 years ago. The CCD cameras, the adaptive optics systems that compensate for atmospheric distortion, the computer algorithms that filter signal from noise, all of this was developed specifically for astronomy. And now these technologies have spun off into other fields. Medical imaging uses algorithms developed for processing astronomical data. Digital cameras in smartphones descend directly from CCDs designed for telescopes. The GPS system relies on precision timing techniques pioneered by radio astronomers. This is how science works in the real world. Pure research, driven by nothing more than curiosity about a distant star, produces technologies that transform society. Nobody funding the development of CCD cameras in the 1970s imagined they'd eventually let billions of people take photographs with devices in their pockets. Nobody designing adaptive optics systems thought about medical applications. But that's what happened. Knowledge begets technology begets more knowledge in an ever-accelerating cycle. HD 189733b sits at the center of this cycle. Every observation of this planet pushes instrumentation to its limits, demanding better detectors, more stable spectrographs, cleverer data analysis. And those improvements don't just help us study this one planet. They enable discoveries across all of astronomy. Better spectrographs let us measure the composition of distant galaxies. More sensitive detectors let us find asteroids that might threaten Earth. The return on investment from studying one weird planet ripples outward through all of science. Now let me tell you about something that's going to revolutionize our understanding of HD 189733b within the next decade: direct imaging. Right now, we study this planet by analyzing light from its star, detecting tiny signals that reveal the planet's presence and properties. But we don't actually see the planet itself. It's lost in the glare of its star, like trying to spot a firefly next to a searchlight. But that's changing. New technologies, coronagraphs and star shades that block stellar light while allowing planetary light through, are being developed right now. Within 10 years, we might have space telescopes capable of directly imaging HD 189733b. Not as a point of light, but as an actual disk. A blue disk. We'll be able to see cloud patterns, watch storms evolve, observe atmospheric features directly rather than inferring them from spectra. Imagine that. Imagine seeing weather maps of an alien world. Imagine watching a storm system the size of Earth form, intensify, and dissipate over the course of days. Imagine tracking individual cloud formations as they race around the planet at thousands of miles per hour. This isn't science fiction. This is what next-generation telescopes will do. And HD 189733b, because it's relatively nearby and transits regularly, will be one of the first planets we image this way. When that happens, when we see actual images of this world, it will transform public perception of exoplanets. Right now, exoplanets are abstractions for most people. Numbers and graphs and artists' conceptions. But an actual photograph, even if it's just a few pixels across, makes it real in a way that data never can. It proves, viscerally and undeniably, that these worlds exist. That we're not alone in the universe. That the cosmos is populated with planets as real and tangible as Earth. But imaging isn't the only frontier. There's also astrometry, the precise measurement of stellar positions. As HD 189733b orbits, it pulls its star in a tiny circle. We've measured this through Doppler spectroscopy, detecting velocity changes. But we can also measure it by tracking the star's position on the sky. With sufficient precision, we can watch the star wobble back and forth, directly observing the gravitational dance between star and planet. This technique, space-based astrometry, will let us detect planets we can't find any other way. Planets that don't transit. Planets too small to create detectable Doppler shifts. Planets in orbits so wide that transits happen once per decade. The European Space Agency's Gaia mission is already doing this, measuring positions of billions of stars with unprecedented precision. The data from Gaia will reveal thousands of planets, including potentially other planets in the HD 189733 system. And here's something that gives me chills: we might discover that HD 189733b has a massive moon. Not like the moons we've discussed that probably existed and were destroyed, but a moon that survived. A moon massive enough to have its own atmosphere, its own weather, its own geological processes. Such a moon, if it exists, would be incredibly rare, would challenge theories of moon formation and survival in extreme environments. The probability is low. Most moons that close to a star would be stripped away by tidal forces or would have crashed into the planet. But not zero. And if we find one, it would be extraordinary. A natural satellite orbiting a hot Jupiter, heated by both the star and tidal forces from the planet, possibly even more extreme than the planet itself. It would be a laboratory for studying moon formation, tidal evolution, and atmospheric dynamics under conditions we've never encountered. Let's shift gears and talk about the star itself, because HD 189733a, the orange dwarf at the center of this system, is fascinating in its own right. It's a K-type star, cooler and dimmer than our Sun but more common in the galaxy. K-dwarfs have some interesting properties that make them attractive targets in the search for life. They live longer than Sun-like stars. Much longer. While our Sun will last about 10 billion years total, K-dwarfs can shine for 20 to 40 billion years. That's 2 to 4 times longer for life to emerge and evolve. If you're looking for ancient civilizations, planets around K-dwarfs are where you'd start. They've had more time to develop complexity, more opportunities for intelligence to arise. But they're also more active when young. K-dwarfs spin faster and have stronger magnetic fields than mature Sun-like stars. This creates more star spots, more flares, more coronal mass ejections. We've observed HD 189733a during several large flares, events that would be catastrophic for any planets in the habitable zone. The X-ray and ultraviolet flux increases by factors of hundreds or thousands, bathing nearby planets in sterilizing radiation. This is the paradox of K-dwarfs. They offer more time for life to develop but subject planets to harsher conditions, especially during the star's youth. For the first billion years of the system's existence, HD 189733b would have been bombarded constantly by flares. The atmospheric escape rate we observe today is probably mild compared to what it was in the past. The planet might have lost several times its current atmospheric mass in those early years. And yet it survived. Massive enough, with gravity strong enough, to hold on despite the onslaught. But any smaller planets, any potentially habitable worlds that might have existed, probably weren't so lucky. They would have been stripped bare, reduced to barren rocks orbiting a hostile star. This is the cruel reality of planet formation around active stars. Time favors the development of life, but violence works against it. There's a concept in astrobiology called the continuously habitable zone, or CHZ. It's not just where liquid water can exist now, but where it could exist continuously for billions of years. Because stars evolve. They get brighter as they age. The habitable zone moves outward. A planet that starts out habitable might become too hot. A planet that starts out frozen might thaw and become habitable later. For K-dwarfs, the CHZ is narrower than for Sun-like stars. The star's evolution is slower, so the zone doesn't move as much, but the zone itself is closer to the star because K-dwarfs are dimmer. And being close to an active star means more radiation, more tidal effects, more atmospheric erosion. Finding a planet in a K-dwarf CHZ that has actually remained habitable for billions of years is challenging. HD 189733 has no planets in its CHZ. If it ever did, they're gone now, destroyed during the formation and migration of the hot Jupiter. This system is sterile. Not because it couldn't support life in principle, but because the dynamics of planet formation created a configuration hostile to biological processes. And this might be common. Hot Jupiter systems might represent a significant fraction of stars where life is impossible not because of stellar properties but because of planetary architecture. Here's a number that puts things in perspective. Astronomers estimate that between 5 and 15% of Sun-like stars host hot Jupiters. That's a substantial fraction. If the same percentage applies to K-dwarfs, and if hot Jupiters destroy habitable planets during migration, we're talking about billions of sterile systems in the Milky Way alone. Billions of stars that might have hosted life but don't because gravitational chaos intervened. This is depressing but also informative. It tells us that the universe isn't uniformly hospitable to life. There are selection effects, filters, catastrophic events that prevent some systems from ever developing biology. Understanding these filters is crucial for estimating how common life is. Every constraint we identify, every mechanism we discover that reduces habitability, refines our estimates and helps us understand what makes Earth special. But let's not be entirely pessimistic. Because there's another side to this story. Systems without hot Jupiters, systems where gas giants stayed in the outer solar system where they formed, are probably more stable. More conducive to the long-term survival of rocky planets. Our solar system is one of these. And if hot Jupiters are present in only 10% of systems, that means 90% avoided this fate. 90%. That's a lot. If there are 400 billion stars in the galaxy, and 90% of them lack hot Jupiters, that's 360 billion stars where habitable planets might exist undisturbed by migrating giants. The numbers still favor life. Abundantly. HD 189733b represents the exception, the catastrophe, the worst-case scenario. Most stars, most systems, don't end up this way. And even in systems with hot Jupiters, life might find a way. Not on the hot Jupiters themselves, but on planets that formed after the migration phase. Or on moons. Or in asteroid belts where organic chemistry creates complex molecules that seed planets later. Life is tenacious. It exploits every niche, every opportunity, every loophole in the laws of physics that permit its existence. Writing off hot Jupiter systems entirely might be premature. There's also the question of panspermia, the idea that life can spread between planets or even between star systems. If microorganisms can survive in space, shielded inside rocks ejected from planetary surfaces, they might colonize new worlds. A hot Jupiter migration event would eject enormous amounts of material from the inner system, asteroid fragments, comet nuclei, possibly even chunks of planetary crust blasted into space during collisions. Some of that material would escape the system entirely, carrying whatever microorganisms existed with it. This ejected material could travel through interstellar space for millions of years before encountering another star system. Most of it would be sterilized by cosmic rays and ultraviolet radiation. But not all. Some microbes, protected deep within rocks, might survive. And if they landed on a habitable planet in another system, they could seed it with life. In this scenario, the catastrophe that destroyed habitable worlds in one system could create habitable worlds elsewhere. Life spreads not despite chaos but because of it. Is this speculation? Absolutely. We have no evidence that panspermia occurs between star systems. But it's plausible speculation, consistent with what we know about microbial survival and interstellar material transfer. And it reminds us that the universe might be more interconnected than we realize. Systems that look sterile today might have exported life elsewhere. HD 189733b might be a graveyard, but the remains could have fertilized gardens light years away. Now let's address something fundamental: why do we care? Why invest billions of dollars and decades of effort studying a planet we'll never visit? What's the point? The immediate answer is knowledge for its own sake. We study HD 189733b because it's there, because it's interesting, because understanding it satisfies human curiosity. That's valuable in itself. But there are practical reasons too. Studying extreme planets improves our models. Those models apply to all planets, including Earth. Understanding atmospheric circulation on HD 189733b helps us understand circulation on Earth. Studying tidal effects on hot Jupiters informs our understanding of tidal effects on exomoons and even on Earth-Moon dynamics. The physics is universal. Lessons learned from alien worlds apply at home. There's also technological spin-off. Every instrument developed for exoplanet research finds applications elsewhere. Spectroscopy techniques used to study planetary atmospheres are now used in environmental monitoring, detecting pollutants and greenhouse gases in Earth's atmosphere. Algorithms for extracting planetary signals from noisy data are used in medical imaging, financial modeling, and machine learning. The return on investment is difficult to quantify but undeniably positive. And there's inspiration. HD 189733b inspires young people to study science. It captures imagination in ways that abstract physics or chemistry problems don't. Kids who learn about glass rain and hypersonic winds on an alien world might decide to become scientists or engineers. They might invent technologies we haven't imagined yet. They might solve problems we don't even know exist. Inspiration compounds over generations, creating cascades of innovation that trace back to moments of wonder sparked by discoveries like this. But the deepest reason we study exoplanets is philosophical. We want to know our place in the universe. We want to know if Earth is common or rare. If life is ubiquitous or unique. If intelligence is inevitable or a cosmic accident. These questions have no economic value. They don't cure diseases or improve crop yields. But they shape how we see ourselves, how we value our planet, how we think about our responsibility to future generations. HD 189733b teaches us that Earth is precious. Not because some deity placed us here, not because we're at the center of creation, but because the specific set of circumstances that created our world is rare. Maybe not unique, but rare. Rare enough that we should cherish it. Protect it. Treat it with the reverence it deserves. When you look at HD 189733b, when you contemplate a world of eternal fire and glass rain, you gain perspective. Earth's problems, climate change and pollution and habitat destruction, seem more urgent when you realize there's no backup planet. There's no other world waiting for us if we destroy this one. We have one chance. One fragile oasis in a cosmos filled mostly with nightmare worlds. This realization should motivate action. Not paralysis. Not despair. But urgent, determined effort to solve the problems we face. Because if we fail, if we render Earth uninhabitable, the universe won't care. It will continue its indifferent expansion, creating hot Jupiters and rogue planets and all manner of weird worlds, none of which give a damn whether humanity survives. But we care. And caring, that uniquely human capacity to value things beyond immediate survival, to work toward distant goals, to sacrifice present comfort for future benefit, that's what makes us special. Not our intelligence per se, but what we do with it. How we choose to use our understanding of the universe to create meaning, purpose, and legacy. Let me leave you with this final thought. Right now, at this very moment, photons are leaving HD 189733b. Photons that have bounced off silicate clouds, passed through layers of hot gas, and escaped into space. They're traveling through the void at the speed of light, carrying information about that planet's current state. In 63 years, those photons will arrive at Earth. Someone, somewhere, will capture them with a telescope. They'll analyze the light, extract information, and learn something new about that distant world. That person might be you. Or your children. Or your grandchildren. The story of HD 189733b isn't finished. We're still writing it. Every observation adds another chapter. Every discovery raises new questions. Every answer leads to deeper mysteries. This is the beauty of science. It's not a static body of facts. It's an ongoing conversation with nature, a dialogue that spans generations, that builds on what came before and paves the way for what comes next. HD 189733b is one voice in that conversation. A strange voice, speaking in a language of glass and fire, but a voice nonetheless. And we're learning to understand it. The universe is vast beyond comprehension. 400 billion stars in our galaxy alone. 2 trillion galaxies in the observable universe. More planets than grains of sand on all the beaches on Earth. And we've studied, in detail, just a few thousand of them. We're at the beginning of planetary science, not the end. The strange worlds we've discovered so far are probably the least strange. Weirder planets await, pushing the boundaries of what's physically possible even further. HD 189733b is our teacher. It shows us what's out there. It demonstrates that nature is more creative than fiction. It proves that the universe doesn't constrain itself to human intuition. And it reminds us that we're part of something larger than ourselves, participants in a cosmic story that began billions of years before we existed and will continue billions of years after we're gone. But for this brief moment, this cosmic instant during which humanity exists and looks outward, we get to observe. We get to measure. We get to understand. We get to marvel at glass rain and hypersonic winds on a blue planet orbiting an orange star in the constellation Vulpecula. We get to be the universe's consciousness, the means by which matter becomes aware of itself. That's not a small thing. That's everything. HD 189733b is 63 light-years away. We'll never touch it. Never visit it. Never feel its impossible winds or see its alien sky firsthand. But we don't need to. Because we've done something better. We've understood it. We've measured it. We've made it part of our story. And in doing so, we've expanded the boundaries of human knowledge, pushed back the darkness of ignorance just a little bit further, and reminded ourselves why we look up at the stars in the first place. Not because we're running away from Earth's problems. But because we're running toward understanding. Toward knowledge. Toward that distant horizon where questions outnumber answers and every discovery reveals how much more there is to learn. The strangest planet NASA ever found is a reminder that strangeness is the universe's default state. Earth is the anomaly. Calm weather, liquid water, stable temperature, protective magnetic field, all of this is unusual. Rare. Precious. And recognizing that preciousness, understanding our cosmic luck, appreciating the razor's edge between existence and oblivion, that's what studying HD 189733b ultimately teaches us. We are here. Now. In this moment. On a planet that doesn't rain glass. Under a sun that doesn't flare catastrophically. In an atmosphere we can breathe. With temperatures we can survive. This is a gift. Not from anyone, but a gift nonetheless. A statistical miracle. A roll of the cosmic dice that came up in our favor. And the proper response to that gift isn't to take it for granted. It's to cherish it. Study it. protect it. And use our brief time in the sun to push human understanding as far as it can go. To catalog the strange. Embrace the impossible. And never, ever stop asking why. Because out there, orbiting 1,000 suns, are 1,000 worlds stranger than HD 189733b. And we're going to find them. We're going to study them. We're going to understand them. Not today. Not tomorrow. But eventually. Because that's what humans do. We reach. We explore. We discover. And 63 light-years away, indifferent to our observation but central to our story, a blue planet races around an orange star, its glass cloud streaming in hypersonic winds, its atmosphere bleeding into space, existing simply because physics allows it. A nightmare world that has become, through our understanding of it, something beautiful. A testament to the power of science. A symbol of human curiosity. And a mirror that shows us, not what we are, but what we could have been if the dice had rolled differently. The strangest planet NASA ever found is strange only because we survived to find it strange. And that makes us the luckiest species in the galaxy. At least, so far.